Hi, my name is Lekha Srinivasan, and in this video, I'm going to talk about a new emerging technology called the vertical NAND or 3D NAND flash memory. Let me begin by outlining all the topics that are going to be dealt in this presentation. Initially, we shall understand the concept of 2D NAND, which is the traditional technology used in flash memory cells. This technology has got a lot of drawbacks, and that has led to the development of the 3D NAND. Next, in this presentation, we shall understand the basic concept of the 3D NAND cells and also see how charge is stored in this technology. Two architectures are also introduced in this presentation. The advantages and disadvantages along with the recent advancements are also presented before we conclude. Flash memory is widely used as data storage in commercial devices and is the most important component in any solid-state drives. Low cost and high storage capacity are the two most important features which are desired in any memory technology. In order to achieve this, semiconductor manufacturers have aggressively scaled down the NAND cell size so that they can pack more NAND cells within a limited space. More cells implies more storage capacity. This trend, however, has saturated and we have reached our scaling limit, and alternating approaches to improve the storage capacity are being explored. One solution is the V-NAND. The 2D NAND or the planar NAND is a traditional architecture used in flash memory. Here, the memory cells are arranged side by side on a silicon substrate. It can be seen that on packing more cells on a single substrate, we can increase the bit density and thus we can have more memory capacity. Over the last decade, flash memory has focused on trying to increase its memory capacity, increase its speed, and lowering its bit cost. In order to achieve this, semiconductor manufacturers have focused on scaling down the 2D NAND cells so that they can pack more NAND cells into a given substrate. This trend, however, has reached its saturation, and now we have got a lot of drawbacks for these 2D NAND. One of them being cell-to-cell interference, because NAND cells are being placed so close to each other, there has been errors and data retention problems. Also, we require a lot of advanced lithographic tools, and there has been problems with read noise, which has decreased the performance of the NAND cells. To overcome this, the 3D NAND is being introduced. The obvious solution to the scaling problem is to add and stack memory cells vertically in a new dimension. And this is the basic concept of the 3D NAND. These vertical layers allow for higher bit density per unit area without requiring smaller individual cells. Thus, we can achieve more capacity within a smaller footprint. The basic function of any NAND flash memory is to store charge for writing and sense charge for reading. Charge retention can be done by two techniques, which are the floating gate technique and the charge trap technique. In the floating gate technique, the storage node is discrete and this ensures that each cell is physically separated from the other. The charge trap technique has got its storage nodes which are continuous, and this ensures that each cell is physically bound to the others. Traditional 2D NAND uses the floating gate technique, and initial 3D NAND cells also used the floating gate techniques. However, due to certain limitations of the floating gate, newer 3D NAND technologies prefer to use the charge trap technique. The floating gate technique has the main advantage that it offers better data retention. However, this technique has got a lot of drawbacks. The first being that as the cell size becomes smaller, it is more susceptible to disruptions. Additionally, it involves difficult patterning steps, and it becomes especially hard to pattern things on the side of a vertical hole. The main advantage of charge trap technique is that the silicon nitride used is less susceptible to defects and leakage. Also, this approach enables faster read and write operations, as well as lower energy consumptions. Hence, the charge trap technique is more dominant. Let us explore different architectures of the 3D NAND. Two popular architectures include the bit-cost scalable V-NAND and the terabit cell array transistor V-NAND. The BIGS is the earliest 3D NAND implementation and employs a punch and plug process for its fabrication with gate-first mechanism. The TCAD was announced in 2009 and it employs a gate-last mechanism. Understand more about the bit-cost scalable 3D NAND. The figure 4 here gives a clear view of its architecture. As you can see, we have got multiple stacks of memory arrays laid one on top of the other. These stacks have holes punched in them, and on plugs found on these holes, strings of cells are attached vertically. The plugs pass through the holes, and at the bottom they are connected to the source diffusion of the substrate. The bottom layer here serves as the select gate, while the upper layer serves as the control gates, and the topmost layer is the upper select gate. The edges of the control gate layers have a staircase-shaped structure. These are linked to several rows of strings, decreasing the amount of control transistors needed, and therefore the area, even though the number of layers is increased. Next, let us understand the basic idea of the TCAD architecture. Figure 5 shows the bird view of its architecture. As you can see, it is very similar to that of the bit-cost scalable architecture. The bit-cost scalable architecture, however, has got a lot of disadvantages, and the TCAD architecture overcomes these. These differences can be illustrated in the figure 6. Since the TCAD is based on a gate-last mechanism, the charge trap layer is bioconcave, making it more difficult for charges to spread out. The BIGS, on the other hand, is distinguished by charge trap layer that runs along all the gate plates, serving as a charge spreading path. This has a disadvantage as it results in reduction in data retention. Another difference from the bit-cost scalable architecture is that the layer stack in the TCAD is formed by sacrificial nitride or oxide rather than polysilicon or oxide. This TCAD architecture is what is presently used in most of the 3D NAND architectures. From the above slides, we can clearly see that the 3D NAND has got more advantages than the 2D or the planar NAND, which is traditionally used in flash memory. Some of the advantages are that the 3D NAND provides higher memory capacity in a smaller space. It lowers the cost per gigabyte. It reduces the cell-to-cell interference, which is a very important issue in 2D NAND. It improves the performance with less power consumption. It boosts reliability and provides high data writing performance. Clearly, 3D NAND is a winner. However, there are certain disadvantages associated with 3D NAND. It has got high manufacturing costs. It has got complex error collection codes and flash management. As we need more stacks, 3D NAND need more silicon, which poses as an issue. Also, the 2D NAND environment now needs to be replaced with a 3D NAND, which seems to be a bit more expensive. However, due to the advantages of the 3D NAND, 3D NAND is more preferred. Let us see the advancement of the 3D NAND technologies over the last couple of years. The initial 3D NAND introduced was a double-stacked planar cell structure in 2006. The BICS architecture, which was discussed previously, was introduced in 2007, while the TCAD was introduced in 2009. Very recently, Micron and Intel certified their first ever multi-level cell floating gate technology for the 3D NAND. And in 2018, they qualified their industry's first 3D NAND quad level cell floating gate technology. Manufacturers have been racing each other to increase the number of stack layers. Presently, we are having 128 layers, and now we have reached 276 layers. Very recently, in 2020, Micron and SK Hynix took the technology lead to moving into 176 layer 3D NAND products. In conclusion, we can see that the 3D NAND is a potential replacement for the planar NAND technology, and it overcomes the scaling and reliability problems of the 2D NAND. The floating gate and charge trap techniques are used by the V-NAND technology, and semiconductor manufacturers are competing to demonstrate their feasibility when scaling is pushed to the maximum. The future of tray NAND is trending towards increasing the number of stack layers, and even though the production sequence can be quite challenging with respect to the number of stack layers, the future of 3D NAND looks promising. Before concluding this presentation, I would like to show you all the papers that I referred to in order to make this presentation possible. Thank you.